In this video, I introduce denoising diffusion probabilistic models in machine learning. Diffusion probabilistic models are latent variable models p theta, where x from 1 to t are latent variables, and joint distribution p theta is a reverse process that is a Markov chain with learned Gaussian transitions p theta starting at p theta xt as shown here. This is a joint distribution and this is a Gaussian transition and explained in this figure. Forward process posterior Q is a Markov chain that gradually adds Gaussian noise to the data according to a varying schedule from beta 1 to beta t, as shown here. Using important sampling, training is performed by optimizing the variational bound on negative log likelihood, as shown here. For small hyperparameters beta t, the forward and reverse processes have the same function form. Defining alpha t is 1 minus beta t and alpha t bar. Here, the forward process q at xt is defined here. Variational bound of the negative log likelihood is split into three terms, namely LT, LT minus 1, and L0 as shown here, which uses KL divergence to compute p theta against the forward process posterior q, which is tractable when condition on x0, as shown here. For KL divergences, in negative log likelihood becomes a comparison between Gaussians, so that they can be analytically calculated using Raw-Blackwell theory. The first term LT in the expectation is constant and it is ignored during training. The problem now becomes how to sample the reverse process transition p theta. If selecting the variance sigma theta, choice here is for normal distribution x0, and this choice is for 1 point x0. Denoising diffusion model. Denoises are corrupted distribution px t to go back to the original distribution qx0, as shown here. Using sigma theta here in the p theta, the second term Lt minus 1 is the expectation is written as denoising score matching objective, as shown here. This score-based model and this denoising score matching model, where the constant c disappears in gradient operation. Parameters theta of the model mu theta are optimized to predict the forward process posterior mean mu t tilde. By using epsilon to reparameterize in xt, for epsilon is a normal distribution, the denoising score matching objective Lt minus 1 is rewritten as here, which means that the model mu theta predicts this value at a time step t given xt. Since xt is available, learning the model mu theta becomes the learning of function approximator epsilon theta as shown here, where epsilon theta predicts epsilon from xt. Samples xt minus 1 are computed from this sampling, where z is a normal distribution. The denoising score matching objective L t minus 1 is further simplified as here, which resamples denoising score matching over multiple noise scales indexed by t. The reverse process mean function approximator epsilon theta is trained to predict epsilon by reparameterization. The last term L0 of the reverse process is derived from a Gaussian distribution here, which can be combined with Lt minus 1. The final denoising score matching objective is written as here, where t is uniform between 1 and capital T. T equal to 1 corresponds to L0 and t larger than 1 corresponds to Lt minus 1. Here is a pseudocode of our model training. For more details, please check with these references. Thank you.